Hello, my name is David Maletich, and for today's adventure, we're going to talk about inlet boxes. Specifically, how an inlet box can change or alter the way a fan performs. Thanks. Whether we're at home or at the job site, we have to be concerned with safety. We're dealing with sheet metal. Sheet metal can have sharp edges on it, so we want to make sure that we have hand protection during our presentation. Thanks a lot. Let's talk about the demo equipment used for our little adventure today. First, we have a fan, open inlet. We have a rectangular round transition, round piece of ductwork. In that ductwork, we have a pitot tube. I know you can't see it, but attached to the pitot tube is this flexible tubing here that goes to our Magnehelic gauge. We have an outlet damper on the fan. Outlet damper is set to generate about 1 inch of resistance or 250 Pascal on our gauge. That'll be our benchmark setting for the fan with the open inlet. Finally, we have 2 different inlet box designs that we'll use to demonstrate how they change or alter the way a fan performs. Thanks a lot. Let's move on to the demo, the reason why you're actually watching this video. As you can see, fan is on. Baseline number is 1 inch of water gauge or 250 Pascal, open inlet. Let's see what happens when we add an inlet box to the fan. When we look at this inlet box, it's just a box, nothing in it. However, it does have a poor aspect ratio. Its depth compared to its width is very narrow. It's very small. And let's see what happens when we put this on the fan. Looking at the Magnehelic gauge, you'll notice a couple things. One is, it's a pretty substantial loss when we put this box onto the fan. Secondly, you'll notice that the needle on the Magnehelic is bouncing up and down. It's not at a steady state. That means that we've created turbulent flow with this fan, and we've actually pushed this fan into an unstable region on the fan curve. That's going to be a problem if you have an application that requires very steady flow. Like, so for example, if you have a combustion air system, that can cause some pretty big issues with the flame that's being used to heat the process. And then finally, audibly, you notice that there's some droning effects with this, that as that needle goes up and down, the sound of the tone or sound tone of the fan goes up and down as well. It kind of goes, And that's also an indication that the fan is operating in an unstable region. So let's look real quickly as to what's happening. Again, air has mass, so that mass wants to go in a straight line as it comes down, hits the bottom of this duct box, and then bounces back up. And we're only utilizing the bottom portion of this ductwork. The top region never sees any air. Because of the poor aspect ratio, air is very finely funneled in. So it comes back, it kind of comes down to here, comes down to here. This section on the sides never sees any air. So basically, even though we have the same area, this is a larger duct, that functional area is not used. Now let's see what happens when we put a proper duct on there, or a proper inlet box on there. Notice that the aspect ratio has changed. Its width compared to its depth is much more square-like. That allows for more air to enter into the box and enter into the fan. Secondly, we've added turning vanes to this inlet box. And those turning vanes actually break the box into 3 sections. So we have a section like this, we have a section like this, and that allows the air to come in, load the top, air to come into the middle, load the middle, air to come into the bottom, load the bottom section of the wheel. Let's see what happens when we use this box opposed to this box. Grab my pen so it doesn't fall, sorry. Okay, looking at the Magnehelic, you'll notice that there's a substantial improvement in performance with this box design over this box design. Secondly, the needle or the marker on that Magnehelic gauge is much more steady. It's not bouncing up and down. And finally, Notice the tone of the fan is not droning any longer. It's at a steady state as well, and that's because we're now at a stable operating point on the fan curve. Thank you. Let's move on to final thoughts. An improperly designed inlet box can have not only a negative effect on how the fan performs, but on how the system performs. So if you have a burner, fans in an unstable region on the fan curve, you're going to have a hard time maintaining a consistent flame. Or if you have a fluidized bed, you're going to have a hard time maintaining proper bed depth, and as well as keeping that bed in a fluidized state. If you have a properly designed inlet box, it makes those things much easier. However, the way you design the box also affects how the system operates. So turning vanes, very nice, simple way of properly loading the wheel. However, if you have a bulk material handling application, or if you're moving abrasives, that can either eat away at the vanes or cause the vanes to act as a blockage device. There's ways we can get around that, remove the vanes. We can taper the inlet box in multiple directions to help uniformly load the fan wheel. Thank you. Any questions, comments, put them in the section below. We'll try to respond as quickly as possible. Any other videos you'd like to see us produce, let us know as well. We'll get right on it and start making them. Thanks a lot.